In this screencast, we're going to study the gradient and potential of a vector field. The idea is if you begin with a function, say x squared plus 4xy plus 3y squared, then we have already learned how to calculate a derivative. The derivative of that function is, well, I need to take a derivative with respect to x and a derivative with respect to y. The derivative with respect to x is 2x plus 4y plus 0. And then with respect to y, it's 0 plus 4x plus 6y. That's our derivative. That derivative is a matrix when written in vector form. So if I instead of brackets use vector symbols, 2x plus 4y, comma, 4x plus 6y, then this is given a name and it's called the gradient. The gradient of a function is essentially the derivative. The only difference is we write it as a vector instead of a matrix. Now, the idea of a potential, we've got gradients down. The potential is, well, what if I start with a vector field and I don't know the function that that vector field's the derivative of? Is it possible to recover the function given the vector? So if I just begin with a vector field, namely 2x plus 4y, comma, 4x plus 6y, and I just start with a vector field and I don't know any of the information above, is it possible to recover the function? If so, that function is called a potential for the vector field. So how in the world would you do it? Well, this is supposed to be f sub x. This is supposed to be f sub y. So if you would like to find the original function, then I ought to integrate this with respect to x, and I ought to integrate this with respect to y. So if I integrate this term with respect to x, I end up getting an x squared plus 4xy. That's the integral of the first part with respect to x. Now we're going to integrate this part with respect to y, giving me a 4xy plus 6y squared over 2, or 3y squared. When I integrated this term with respect to x, I should have gotten the original function, but I'm missing a 3y squared. Why am I missing the 3y squared? The answer is, well, when I take a derivative with respect to x, that's 0, hence it disappears. So really there's plus some constant, but that constant could depend on y. Similarly over here, I don't end up getting the x squared term when I integrate because anything that depends on x will be 0 when I take its derivative with respect to y. But notice that the 4xy happens to appear in both integrals. Comes from each of these parts, and the reason it does is because it has both an x and a y in it, hence it should appear in both parts. If I want to recover the original function, then the idea is I'll just take the x squared plus 4xy, but since the 4xy appears in both, it ought to because it has both an x and y in it. Don't include it, just ignore it, and then add on the 3y squared. Essentially, you integrate each term with respect to this one with respect to x, that with respect to y, and then sum the results ignoring duplicate terms. That is called a potential for f. A potential is a function, I'll just write that down, a potential is a function, little f, such that the gradient of little f equals the vector field. And that's what a potential of a vector field is. Let's look at one more example before we finish. Let's just take another vector field. Suppose the vector field is 2x plus 3y plus 4z. And then we'll go 3x plus 4y plus 5z. And then 4x plus 5y plus 6z. Does this vector field have a potential? Well, this ought to equal f sub x, this ought to equal f sub y, and this ought to equal f sub z. So I'm going to integrate this with respect to x, giving me x squared plus 3xy plus 4xz. This one I'm going to integrate with respect to y, giving me a 3xy plus 4y squared over 2 plus 5yz. This one I'm going to integrate with respect to z, giving me a 4xz plus 5yz plus 6z squared over 2, or 3z squared. Now, this term only has an x in it, so I'm going to write it down. This term has an x and a y, which means that it better appear in both the x and the y spots. It does, so I don't need to write it twice. 3xy. This term has an x and a z, which means it ought to occur in the z part. It does, so I won't write it down twice. I keep going. That part we already wrote down. This only has a y, so it should only appear in the y spot. It's a 2y squared. This has a y and a z, so it ought to appear in both. It does. I won't write it down twice. And then the last term is the 3z squared. This function, what is its gradient? Well, if I calculate the gradient, its gradient is 2x plus 3y plus 4z plus 0 plus 0 plus 0. If I take the derivative with respect to y, then I get 0 plus 3x plus, I'm taking derivatives with respect to y, so that's a 4y, and that's a 5z, and that's a 0. And now with respect to z, I get a 0, 0, 4x plus 0 plus 5y plus 6z. And the gradient equals the function. So how do you find a potential? You integrate each term, you ignore replicate terms, and you sum the result. And that completes this.